morning to all of you. Thank you, Professor Kailasnath, for the nice introduction. And I would also like to thank the organizer for inviting me and giving me the opportunity to share my work with you. So my topic is asynchronous quenching, a mechanism of open loop control of thermoacoustic instability. So thermoacoustic instability, I mean the background is nicely set by Dr. Pillai. So let me just go on. So these are my collaborator, Amitesh Roy, Dr. Samadhan Pawar and Professor R.I. Sujit. He is my mentor during my postdoc. And the work is actually done in IIT Madras with the funding of ONR Global. So basically this strategy or the mechanism, the concept is basically coming from the synchronization theory. And that theory is well developed by the physicist. So the synchronization theory is essentially deals with the interaction between oscillators, right? So here we are going to test this concept, this asynchronous quenching, with two different thermoacoustic systems. So one is Riquet tube, which is again a very prototypical thermoacoustic system people generally use to investigate thermoacoustic instability. And then other one is again, you can call it vertical Riquet tube, but the difference is in the Riquet tube we don't have flame. So instead of flame there is electrically heated wire mesh, and here there is a flame inside a duct. So yeah, so everything that background has already set. So it's basically there is a high amplitude of pressure oscillation, and that is known as thermoacoustic instability, which happens due to the positive feedback between acoustic oscillation inside the combustion chamber and also the dynamics or fluctuation of heat release rate. Now when this acoustic energy grows, that depends on the condition which is represented in this equation. So the condition one is you have to have the instantaneous phase difference between these two oscillations, pressure and heat release rate, that should be in between minus 90 to 90 degrees, so that this left hand side becomes a positive quantity, that is the acoustic driving. So that is known as the Rayleigh criteria. And the second condition is the total acoustic driving of the combustor should be greater than the total acoustic loss. So in such situation there will be growth in acoustic oscillation or high pressure oscillation, and that is dangerous, and there are a lot of catastrophic consequences. It can lead to structural damage and the reduction in the life of the combustor. So because of that there are several studies which basically focusing on the control of such instability or oscillation. So they can be generally classified as passive and active control, and then active control strategy further classified as closed loop and open loop control. So passive control essentially involves the design changes. So they essentially involve the use of baffles, resonator, dampers, etc. And they actually target to either reduce the total acoustic efflux or acoustic loss, or to disrupt the phase relation between pressure and heat release rate oscillation, so that there is no thermoacoustic instability. Whereas in closed loop, so basically the passive loop strategies are kind of trial and error method. So you have to have lot of different design. So one example is this F1 engine for moon mission, which had to go through the more than 2000 full scale test before the actual injector baffler configuration could be finalized. Then in active control there are closed loop control, where basically the real time feedback is needed. And for example, you can use the adaptive choker plate, which essentially alters the acoustic boundary condition. Or you can also use the harmonic driver. Generally you are sending a sound which is the frequency of thermoacoustic instability, and so it is also called anti-sound or anti-phase sound. So these strategies are, they show promise, but they are not used very extensively. On the other hand, open loop control also uses the forcing or the external excitation, and which are used a frequency which is non-dissonant, which is away from the thermoacoustic instability frequency, and there is no real-time feedback. So thereby the designing of such strategies are cheaper and easier. So they have also tested in different studies. So just to give you an example, this is also tested in premixed combustor. So swirl stable is premixed combustor, and they have shown that for some selected frequencies which are non-resonant, so they found this particularly this thermoacoustic mode which is getting suppressed, where this is the driven oscillation or the external frequency which is there still. So in amplitude spectrum you can see this, the mode of thermoacoustic oscillation is completely suppressed, but if you look at this RMS oscillation or the RMS amplitude, I mean it will not go to the zero, but there will be some little amount of oscillation still be there with this open loop control. So this study has, I mean, shown that some selected frequency which are leading to the mitigation of thermoacoustic instability to up to 60% or 70%. So here is the gap. Basically there should be a systematic investigation, the clear picture, which frequency we should choose for open loop control, and that will lead to the maximum mitigation of thermoacoustic instability. So we start with this system first. So where basically there is no flame, so electrically heated wire mesh which is placed in a duct, and because of this coupling there will be sound, so thermoacoustic instability. And with this setup we are not changing anything, any parameter related to thermoacoustic instability. We are positioning the this heater and flow rate, etc., so that we have thermoacoustic instability. And then there is 4 wall mounted speakers through which we are sending the excitation, the sinusoidal excitation. And we are also having a reduced order model. With that also we are checking. So this is basically so this eta j and eta dot j is the time varying coefficient for acoustic velocity and acoustic pressure. And then with this pressure equation, I am just adding a sinusoidal term. Right, so this is just mimicking this experimental, the forcing in the experiment. Right, so before going into the effect of forcing on the thermoacoustic instability, let me just give you what is the behavior of a Riquet tube. So if you so any parameter you can choose, but if you just use the parameter that is heater power, if you are increasing the heater power, so up to this value of heater power, there is a steady, steady flow, or there is no sound actually. But as we just cross this, there will be the pressure oscillation is jump into this value. So this is just PRMS. So basically the high pressure oscillation start to set in at this. And if you just go back from the higher value to lower value, you have to go farther back to come down to the steady state. So this is something which is known as subcritical Hopf bifurcation. And so there is some hysteresis zone is there, which is the characteristics of subcritical Hopf bifurcation. So in this experiment we are not changing anything, everything we are setting these values, so that we have thermoacoustic instability here which is away from the bistable zone. Because during the experiment when we are changing only forcing parameters, either forcing amplitude or forcing frequencies, we should not get into this zone, so that in this zone basically the stability depends on the initial condition. So once it goes into the steady state, it may not come back to the oscillatory state. So we are setting the system further away from the bistable zone in the LCO regime, and we are only changing the forcing parameters. So for this particular experimental setup, this is the natural frequency 168.8 Hertz. So how we did the experiment? So we basically change, in one set we change, keeping the frequency of forcing fixed, we changing, so keeping the amplitude fixed, we changing the forcing frequency across the natural frequency of the Riquet tube. And then we are keeping the forcing frequency fixed and changing the amplitude, and then we are also doing this in both sides of this natural frequency, left and right side. So, and we are going to check the interaction between the self-sustained oscillation in the Riquet tube and the forcing oscillation. Right, here comes the theory of synchronization, because we have now 2 oscillators. So once a system there is thermoacoustic instability sets in, we can consider this as an oscillator, a periodic oscillator, and the external excitation, which is again sinusoidal, that can be also considered as an oscillator. So now these two oscillators are interacting. So when they are interacting, and this interaction is unidirectional because it's a forcing. So forcing will affect the system, but system will not affect the forcing. Right? So in such a situation, the theory says that there should be a synchronization boundary that is which take the form of B safe, which is also known as Arnold tongue. Right? That essentially means inside this tongue, this forcing and the self-sustained oscillation will be synchronized. They will be phase locked, and outside that there will be several different dynamical states. So our objectives is basically to find out where the suppression is going on, or where the whatever the amplitude of oscillation, self-sustained oscillation, how we can reduce that amplitude by forcing. But before that, we need to explore what are the dynamical states that is happening during this transition, when we are changing either forcing amplitude or forcing frequency. Right? So let us take the first case when we are changing the forcing frequency, keeping the forcing amplitude fixed. So when our frequency is far from the natural frequency, right? So here is our forcing frequency, and you can see that the pressure oscillation, this is the response oscillation, is almost periodic, and so basically the forcing doesn't affect the self-sustained oscillation. That is also confirmed by this cluster of points in first return map. And in this plot, so you can see this is the amplitude spectrum of this. So one clear peak is there, frequency peak, and this is the phase difference, the most important plot here, the phase difference between forcing and the self-sustained oscillation. So this is the phase difference between forcing and self-sustained oscillation. So here the relative phase is growing unboundedly. That basically shows this, whatever forcing or excitation I am giving, that is completely desynchronized with the self-sustained oscillation. Now, so this is also known as phase drifting. So because of this is growing unboundedly. So if we come closer to the synchronization boundary, you can see there is a beating kind of phenomena in the pressure signal, and also there is a loop type of structure in the fast return map that basically shows that they are kind of two frequency signals, which is also visible here. So there are two distinct frequency, one is natural frequency, one is forcing frequency. Here in the relative phase plot is showing kind of a staircase like structure. So for a short duration there is a horizontal part which basically shows for sometimes there is a phase locking, and then again it is growing. So this is also known as intermittent phase locking. For sometimes it is locked, and then again there is a called phase sleep or phase jump. And if we go further close to the synchronization boundary, you can see that there is a drastic change in relative phase dynamics. So now this is not at all it becomes bounded. So till the last case it was unbounded, even though it was partly synchronized, but now it is become bounded, but there is an oscillatory nature, and that is what is known as phase trapping. So that essentially means the frequencies are locked. If you find out the mean frequency of both, so they are exactly same. Although this amplitude spectrum is showing there are two different peaks, but their mean frequencies are locked, so they are essentially locked. And at the boundary of this synchronization regime, so you are going to get again the periodic oscillation, because the forcing oscillation and the self-sustained oscillation is completely locked. So these are the dynamics we can have, and if you further go, if you inside the regime, again it is locked, there is only one frequency signal, completely periodic. If you go further, you go through again phase trapping, that is bounded relative phase, then again intermittent, and then phase drifting. Right? So these are the dynamics we are going to get. Now if you look at what is our objective actually, what will be the reduction, or whether there is reduction at all in final amplitude. So we are calculating PRMS of the response signal, and we are seeing that when we are sweeping this forcing frequency, as you are coming closer to the synchronization boundary, the amplitude is reducing, but as soon as we enter into the synchronization boundary, there is a high shoot up of this pressure oscillation. So this is the frequency response curve, you can see this. So this is basically the difference between forcing frequency and the self-sustained oscillation frequency, and that is why this in synchronization region, that is a plateau structure is there. And so this is for one amplitude, one forcing amplitude. If we increase that amplitude, basically this forcing regime is increasing. So that is quite expected, because we are going to have a V type of synchronization regime. So from this plot we can slightly conclude, but I mean we have to refine this conclusion, that if we force the system close to the synchronization boundary, there is a possibility that you are going to have a mitigation of thermoacoustic instability. Okay, so let us now take the second case, when we are basically changing the amplitude, keeping a forcing frequency fixed. So here the forcing, the frequency is 155 Hz, which is kind of away from the natural frequency. So there are two different kinds of dynamical changes happening. So in one, there is, I mean, when is away from the, or the amplitude is very less, that is 3 millivolt, there is again phase drifting. As we are increasing this amplitude 12 millivolt and then 18 millivolt, so it is going through intermittent phase locking and then phase trapping, right? So if you see these two plots, B and C, you can see here the difference in, so this is my forcing frequency peak and this is the natural frequency peak. When you are moving from 12 millivolt to 18 millivolt, basically there is a shift in dominance of frequency. So it was natural frequency dominated oscillation, whereas this is the forcing frequency dominated oscillation, and finally it will get locked with the forcing frequency. So this is when you have your forcing frequency is 155 Hz. Now the second case, taking 167.5 Hz, whereas the natural frequency is 168.8 Hz, which is very close to the natural frequency. So similar kind of dynamics is happening, that is drifting, then intermittent phase locking through locking. The one dynamics is missing is that phase trapping, like when the boundary and oscillatory phase locking is there. And second observation is, if you look at these frequency values, this is 168.8, which is 168.6, 168.5, and then finally 167.5, which is the forcing frequency. So when we are basically increasing the amplitude, the natural frequency is essentially moving towards the forcing frequency and getting locked. So this mechanism is known as phase locking mechanism. Whereas in the previous case, if you look at this, so there is no movement of natural frequency. On the other hand, so when the amplitude of forcing frequency is increasing, basically there is a suppression of natural frequency. So this frequency is going down, and then it completely vanishes. So there are two different routes to force synchronization. So here is the complete map from both experiment and simulation, which basically shows this different dynamical regime. So yeah, so here basically, so this is the first route to the force synchronization, when you are close to the natural frequency, and then there is no phase drifting. It's the no phase trapping. So phase drifting is directly transition to phase locking state. Whereas if you are away from the natural frequency, there is phase drifting, then phase trapping, and then phase locking. Right? So now let us look into the response signals, I mean in terms of the amplitude. So here basically, three different frequency I am showing, this 90 Hz, 120 Hz and 155 Hz, whereas the natural frequency is again, 168 Hz. So we are getting actually both, here the reduction and here the amplification. Now when we are forcing it with a very low frequency, or the frequency which is away from the natural frequency, there is a high level of reduction, and we found that this is maximum 92% of the unforced oscillation. And if you are increasing this frequency, which is coming closer to the natural frequency, still there is a reduction, but reduction is not as high as this one. But when we are actually close to the natural frequency, and there is amplification. So the reason behind this is, so there is definitely suppression of natural frequency that is going down, but at the same time the forcing frequency, there is a resonant amplification, and because of that there is the overall response is getting amplified. So from this point we can conclude that if you want to mitigate thermoacoustic instability, so you have to force it with a frequency which is away from the natural frequency, and even though, so that is what is called the asynchronous quenching, and even though the natural oscillation gets suppressed close to the natural frequency, which is known as synchronous quenching, that will not be helpful because that will associate with the resonant amplification of forcing. So, so this is again this amplitude response when the RMS response when the forcing amplitude is varied. So you can see that up to this synchronization region there is a reduction in amplitude, but as soon as you are going into the synchronization region there is a slight increase, and that increase is very low when you are away from the natural frequency, and this increase is very rapid when you are close to the natural frequency, which is expected because of the resonant amplification. Right, so here basically we are sum up everything, like the maximum reduction that is possible with respect to frequency. So we found that when the frequency is away from the natural frequency, the maximum 85% of 85% reduction is possible with respect to the unforced oscillation, and this is the zone of asynchronous quenching, and asynchronous came from the fact that we are basically forcing it with the frequency which is away from natural frequency. And for this case, but this is not the conclusion, for this particular system we saw that, and this happens only close to the subharmonic frequency. So theoretically it's also possible that in the right side or away from the higher side of the natural frequency it's also possible, but from this system we didn't get that. So let me summarize this. So we have characterized different dynamical state towards the force synchronization or towards the mitigation of thermoacoustic instability, and we found that in V tongue or Arnold tongue the behavior of forcing or the effect of forcing on thermoacoustic oscillation is different when your forcing frequency is less than natural frequency compared to forcing frequency higher than natural frequency. And finally, with this method we have obtained like 85% of reduction in thermoacoustic oscillation, and for this particular system it happened close to the subharmonic frequency. Okay, thank you.
Please identify yourself.
I'm Balasundaram, aerospace department. So I wonder your experiment, how could you translate your observations into a practical gas turbine engine? Because you used speaker and ESOC or heated wire.
Right. So that was the second part of my talk. So the one possibility is so you can modulate your inlet flow. So let me just show you this setup. So this is basically laminar burner, and here we are not using, as you correctly pointed out, speaker you cannot put in the gas turbine engine, but at max you can put speaker in the inlet flow, or you can fluctuate the inlet flow. So that exactly what we are doing here. So in the inlet flow we are basically perturbing the inlet flow, and in that way also we got the same kind of results. But here the complications are more because the heat release rate plays a different kind of form here. So they have heat release rate actually have a different mode, different preferred mode, and because of that basically the mode of heat release rate determines where the asynchronous quenching or the maximum mitigation is possible. But this strategy can be applied, but this is again a very simple setup, right? So we need to turbulent combustor or actual combustor yet to be tested.
Okay. And what about the cost of applicability? Because most of the cost of reliability of your active control, because most of the practical applications they expect it to be a passive control, right? So did you thought about it?
So passive control is always, I mean, very costly, because
Passive,
you have
okay.
to, yeah, definitely. I mean, it's not the, I mean, installation and whatever measurement is, I mean, the equipment is needed, that is very minimal.
Okay.
But how many tested you have to go through, that depends on the maximum cost for practical combustor. Right. So even though, I mean, you can directly suggest that this is the frequency range, this is the instrument, you cannot do that. You have to test. But that test is, I mean, you don't have to change the design of your combustor. So, I mean, that is, that much I can say, that it will be less costly.
Okay, thank you.
Any other comments or questions? If not, let's thanks.